Okay, we are going to wrap up all things integration-esque. We're basically going to learn the last of all the antiderivative formulas that essentially exist. Every time you're asked to integrate something, if you can give me the integral in one step and say this is the antiderivative, there are about 20 of those. We know them because we know how to differentiate going in one direction. Next semester, we're going to learn how to do things where you can't tell me what the integral is in one step. We have to do technique, pull it apart, change it around, stuff like that. But in every problem, we're going to use the antiderivative formulas we're deriving now. So if you look at that formula sheet that I gave you at the beginning that has all the integration formulas, we're going to finish that off today. And some of them are a little bit, difficult to derive, but once we have them, you now have them. You don't ever have to re-derive them. You know a whole bunch of them right now. You know at least a dozen antiderivative formulas, but most of those are fairly simple, right? If I ask you any of the 6 trig functions, if I have the derivative, now if I ask you the antiderivative in reverse, that's supposed to be simple. If I give you something to a power, that should be fairly simple, working backwards and so on. But there are a few that are a little more complicated, and they involve logarithms and inverse trig for the most part. So let's start with what we know. Okay, I'm going to go really quickly here. Let's take the ones we absolutely know. And I'm not even doing chain rule factor yet. All right, I know these 6 trig derivatives. So if I ask you the antiderivative of any of these 6 results, could you tell me? Yes. So I want the antiderivative of negative cosecant squared x dx. Can you tell me this without doing any work whatsoever?
Cotangent.
It's the cotangent of x, and I'll put the plus c. So that's so easy. Then what did we do last day? We said, well, what if it's an argument that's not just an x? Well, then as long as I have the chain rule factor as part of the problem, I can do it. So let me do a similar problem. I want to do negative cosecant squared of, let's say, x cubed dx. I can't do that one, but if I throw in I don't know, how about a 3x squared? Can I do that one? Can anybody tell me the answer without doing any work whatsoever?
X to the third is plus c.
Yeah. This is u, and that's the derivative. So you actually could do this. You said, oh, this is good. I'm going to get really fast at this. Here's the caveat. If that's not a 3, I can introduce the constant. But if that's not a squared, I'm dead in the water. Right? I have to have exactly the right chain rule factor. But that's what we were working on last day. If I have the chain rule factor, it's an easy thing. So if I give you any of these 6 functions right here, you could tell me the antiderivative immediately. That's the whole idea. Do you see anything conspicuously missing on the right-hand side? I have all 6 trig functions on the left. And on the right, I have a cosine, I have a sine, I have a secant squared, I have a cosecant squared, I have a secant tangent, and I have a cosecant cotangent. Do you see anything missing? You should see about 4 things that are missing.
Inverse?
No, just of trig functions. You have a sine and a cosine over there. What don't you have? You don't have a tangent on the right. You don't have a secant on the right. You don't have a cosecant on the right, and you don't have a cotangent on the right, do you? None of my trig derivatives gave me just a secant or gave me just a tangent. Am I right? So here's the question, right? It's the $1,000,000 question. I need the antiderivative of the tangent function. So what derivative gives me tangent? I don't have any tangents on the right. So I'm kind of dead in the water, aren't I? Or am I?
Did you change tangent to quotient to sine?
Oh, I was about to cite the fourth rule of life, and Cece beat me to it. What's the fourth rule of life? Do you remember? If all else fails, you change everything to sines and cosines. You cannot integrate that. But if I change this to sine x over cos x, why can I perhaps integrate this? This was a big theme the last part of class last day. Tell me about my numerator versus my denominator. Isn't the numerator a version of the derivative of the denominator?
So you can do u substitution.
Plus or minus, but do you see that? So I can use a u sub, can't I? Ah. Now, by the way, I said we were missing tangent, secant, cotangent, and cosecant on the right side. In each case, we're going to do a clever substitution. And in each case, the answer is not what you thought it was going to be. So if I do this one and I say, let's let u equal the cosine of x, then what's my d? Negative sine x dx. I have a sine x, I need it to be negative, so I go like this. Negative, negative. That makes it easy. Okay? So this is now of the form 1 over u du, because that whole thing right there is my du. Easy or hard at this point? Easy or hard? Easy. What is it? Negative ln
U.
absolute value. Careful. Can the tangent function ever be negative? How often? Half the time. So, yeah, I need the absolute value. And there's, let me put this, there's a negative. There's a negative there. So now I have negative the log of what? Cosine. Now, everything we said is true, everything we said is correct, but that's not the final answer we want for two reasons. One is I don't like the negative in front. You don't have any antiderivative formulas that have a negative in front of a logarithm. And secondly is the antiderivative of tangent is actually always positive. Now, you're doing an algebra problem, and you got to the end of the problem and you said, and the answer is x equals the negative of negative 6. And let's say that's correct. Does anybody like that as an answer? You said I have the negative of a negative answer. The log of the absolute value of cosine is always negative. And I have a negative in front of it, which means I'm writing an answer as the negative of a negative number, which means that this is not a correct answer because it's not finished. So how do I fix that? Well, now I got to use a log property. And it's one of the simpler log properties, but it's an important one. Do you remember this one? The log of x to the n is n log x. Wasn't that one of our really important ones?
So cos x to the power negative 1.
So if I said, what's the log of x to the negative first?
Negative log x.
Oh, that's exactly what I have, isn't it? So in other words, isn't this the same as the log of 1 over x? So this, by the way, this is an absolute identity. The log of 1 over x is the negative of log x. Now, if x can be, whatever it is, we don't worry about it. But these are an identity. So that means that this is the log of 1 over cos x, which is absolute value, which is the log of secant. And that's the formula that everybody uses. Now, I will have people that will use this, and they'll usually get the wrong answer most all the time, pretty much all the time. No, as you go further in math, you realize you'll never use that ever. Some textbooks have it, some don't. The problem is they're contradicting themselves. This is not simplified. This is always positive, so the log of this will always be a positive number. You can't get a negative answer here. So you don't write a negative in front of something that's always going to be positive, because you have the negative of a negative. Now let's check this answer, just to convince ourselves. I would like to differentiate the log, and I'll just leave it of secant. Well, let's see. I'll do that part. That's my contribution. Right? It's 1 over the thing times Derivative of logarithm is 1 over the thing times
Derivative.
the derivative of the thing. What's the derivative of the thing?
Secant.
Secant tan over secant is
10x.
10. And there's our convincing evidence that yes, we did it right. So the antiderivative of the tangent function turns out to be the log of the absolute value of the secant. Now, you never saw that coming, did you? That the answer to a trig integral is a logarithm? I mean, who knew? That's crazy. But that's what it is. Turns out, of all of the antiderivative formulas you know, log is the most commonly occurring thing in the answer. You didn't see it coming, it just is. Now, what function looks most like tangent in terms of its quotient? Just so we're on the same. What's another function that looks something like
Cotangent.
that? Cotangent. So let's do cotangent. By the way, cotangent is definitely one of the most obscure of all the functions we ever deal with. But I'd like to know how to deal with it. I know how to differentiate it. And by the way, everybody in this room, if you forgot the derivative of cotangent, wouldn't you all change it to cosine over sine and just use quotient rule? Yeah. That would be the smart thing to do if you forgot it. Well, it turns out for the antiderivative, this is just what? Sorry. This is what? Cos x over sine x. Well, let's see. If I do my u substitution here, I think this one's even nicer than the other one. If I let u equal the sine of x, then what's my du?
Cosine of x.
Cos x dx, which is exactly what I have. Huh. So this would be of the form 1 over u du. No negative signs. And the antiderivative of this is? Similar to the last one?
ln
Absolute value of v.
So natural log of the absolute value of the sine function? Really? Could be that simple? Let's check. I want to differentiate the log of the sine function. All right. There's my contribution. What goes on top?
Cos.
The derivative of the sine, and that is, of course, right? Crowd goes wild, confetti everywhere. Well, we don't get that excited over cotangent, but we just figured out how to integrate both the tangent and the cotangent. I'll put this guy up here. Wow, that's awesome. That is really cool. I mean, they're both logs. Anybody want to guess what the form of the other two might involve? Maybe logarithms? Except they're not going to be quite this simple. They are actually quite complicated. Definitely not as straightforward. Question?
Oh, no.
Oh.
I was just,
So, when we are writing the notation for du, do you want us to do du dx is equal to this, and then therefore du is equal to?
No, you can skip that.
Okay.
That is the right question to ask. Basically what Cece is asking is, okay, when that is true, then I know that du dx equals cos x. Absolutely correct mathematically. But when I do the integration, I need to replace this when I replace the variable. That's what this statement is saying. I'm replacing the instruction of cosine with respect to x with the instruction to integrate with respect to u. So you can go directly from here to here.
Okay.
You don't. Now, by the way, I have taught many students over the years that their training in Calc 1 said, no, you absolutely have to do this first. Very strict training. But what I found is when they were very strict, they never made mistakes. It's when we get loose and sloppy, we tend to make mistakes. But this is totally acceptable right here. Understanding this is the in-between step, and then you're going to here. You just don't need to write it twice. You just need to know that that's what's actually taking place. Okay, that's an excellent question. I want to now concentrate on the secant because this is an important antiderivative. The tangent is more common, but the secant comes up, and when it comes up, a lot of times people forget it. Okay? So I want to integrate the secant of x, which obviously is 1 over the cosine of x. So now that should be really easy, right? If my u is cosine, I don't have a du, do I? I can't do a u sub. Won't work. No, I said this one's a little more complicated. What we just did with the tangent and the cotangent worked because when we wrote them as quotients, in both cases the numerator looked like the derivative. But right now the numerator's a 1. That doesn't look like the derivative. So there's something else I'm going to show you.
Never mind.
Oh, okay.
I don't think I know.
Oh, I don't need anybody to know this, but when we see this, you're going to go, this is cool. Now, just for fun, because that is our primary goal, obviously, in class, just for fun, can you differentiate for me the secant of x plus the tangent of x?
Maybe.
Can you do this?
Secant x tan x plus secant squared, which is equal to.
So if this was the instruction, you would give me this and you'd say, oh, but I want to write it in a factored form. Okay. So if I write this in a factored form, it'd now be secant x times what?
Tan plus secant.
Tan x plus secant x. Just to be redundant, would this be the same as saying this? Can I do that?
Yeah.
Yeah, commutativity of addition. Okay, well that's kind of weird. The derivative of this quantity here is exactly secant times the exact same quantity there. This is an observation, that's all I want. Does everyone see that? That's kind of interesting, pretty exciting, right? You'll bring this up at the next party you go to. The derivative of secant, the derivative of secant plus tangent looks like a multiple, literally, of secant plus tangent. Huh. Could I somehow use that to my advantage over here? I don't know. What if I did something like this? First of all, is that legal, what I just did? I just multiplied numerator and denominator by the same quantity. Is it legal? Yes. Why the heck would I do something as insane as that? Because tell me about my numerator compared to my denominator. Isn't my numerator right now exactly the derivative of the denominator? That's what you just did over here. I said this was an interesting observation. Well, it's way more than that now. It's the way I got the answer. I don't know who figured this out, but it was pretty intelligent, whoever did this a few hundred years ago. I multiply top and bottom by this quantity. Why? Because we just showed that the derivative of this is secant times the derivative of this, which just so happens to be my numerator. So right now, if my denominator is u, isn't my numerator exactly the derivative? Yes? No? Maybe?
Yeah.
Yes. I'm going to be really lazy. Can you tell me what my answer is?
Secant x tan x approximately secant x tan x plus secant.
Whoa. Now that is cool. How do I check this? If I differentiate this, then this becomes the denominator, and the numerator becomes the derivative of this. And then they would cancel, getting me back to secant. Isn't that crazy? That's one of the more complicated derivations, but it's beautiful because we just finished it. Yeah.
I know you said you don't know how they figured it out, but how did they figure this out?
You know what I think it was, seriously? There are a lot of times, I don't know if you guys have ever done this, especially when you were kids. You were working with things, maybe it was in class, maybe it was out of class. Maybe you were learning how to do certain algebraic things, and you start just messing around and going, guys, it seems like there's a tendency. Whenever I have something that looks like this, it seems like I get this kind of answer. When you first learned about multiplying conjugates, things of that nature. I remember as a kid, I don't know how, I was just really bored, like 8 squared, 64. Okay, if I go up and down 1, 7 times 9, it's 1 less. If I go up and down again, 6 times 10, it's now 4 less. If I go 5 times 11, it's now 9 less. oh, it seems like every time I go up and down one, the difference of the old one is a perfect square. Well, I just did a plus b times a minus b is a squared minus b squared. In other words, I was seeing a pattern years before I ever heard the term conjugate. I would mess around with numbers and just you'd see things. I think a lot of really important math formulas were discovered by just seeing results and going, gee, I wonder if that's always true. Have you ever asked that question? I wonder if that's always true when you did something? You should. Because if it's true that it's always, then you found a shortcut. I can save myself some time. So I think somewhere, maybe in a calculus class, somebody was doing derivatives and said, you know, I noticed something here. Or maybe they were just really, really, really smart and saw this. I don't know who figured this out because no one's credited with this, but it's pretty smart that they saw this because it's the only way I can answer this question. So the antiderivative of the secant function is this, and that's all we need to remember. Seeing the derivation is important so you know it didn't just come out of thin air. Now the last one is by far the most complicated, the cosecant. We don't love cosecant. Cosecant is not friendly, not particularly. So I want to do the antiderivative of the cosecant, okay? Now, let's do something similar to what we just did here. If I do the derivative of the cosecant plus the cotangent, I want to start by doing the exact same thing. What will I get?
Negative cosecant cotangent plus cosecant, negative cosecant squared.
Good, negative cosecant squared. And if I factor out the negative cosecant squared, excuse me, the negative cosecant, I'll get cotan plus cosecant, or if I write them in reverse order like I did before. So is this going to be a similar result?
Yeah.
Yeah, clearly I'm going to multiply top and bottom by this. Everybody okay with that? Just like we did before. Now, everything we said is true and correct, and this answer is perfectly good. Is there a Pythagorean identity linking secant and tangent?
Yes. 1 plus tan squared is equal to secant.
Yes. 1 plus tan squared equals secant squared. So we know there's something in there somewhere that involves a Pythagorean identity. We don't need it, but we just know there is. Is there a Pythagorean identity involved in the cosecant and cotangent? Well, it turns out it's a similar one. I know that 1 plus the cotan squared of x is the cosecant squared of x. Agreed? Am I okay with that one?
Yes.
Yes? What if I rewrote it just for fun? Again, that's our main theme. Is that true?
Yeah.
I now have a difference of squares. When we were simplifying things at the very beginning of the semester, particularly when you had trig-ish things in your denominator, we often found that multiplying by conjugates made life easier. Can I factor this? Is this true?
Yes.
Huh. I just want to kind of keep that in the back of our minds for a moment. That might come in useful. Might come in useful. I'm not saying it will, it just might. Okay, so going back to this here, I want to multiply top and bottom by exactly cosecant x cotan x. So, except there's one more thing I need.
Negative.
I need the negative, so what do I do? Go negative, negative. Yes?
Yes.
I'm going to be lazy like I did on the last one. Can I go right to here?
Yeah.
Yeah, the numerator right now is exactly the derivative of the denominator, which means my answer is exactly this. We have a similar problem to what we did with the secant, and that is that quantity on the right. I don't like the negative of that. I'd rather this just be a logarithm if possible. You don't want any antiderivatives involving log to ever have a negative in front. But that's not entirely useful. So plus c. Let me ask you a question. I'm going to put a question mark. I showed you this before. Is this true?
Yes.
Do you like that answer?
No.
No, you hate that answer. You'd rather have the one before, except you're never going to see this answer anyway. You're never going to see that one. But you're never going to see this one either. Oh, let's go back over to here, shall we? True or false? A times B equals C. So C equals 1 over B. Is that true? I just divided both sides by that quantity. Is this true?
Yeah.
Yeah, this is always true. Why would I do such a crazy thing? Because this is the thing right now that lives inside the logarithm, and I'm going to replace it with this one. And this is the formula you're going to see in every calculus book, because there's no negative in front. And the only way we got the last one was to use the Pythagorean identity. Again, way beyond clever. Now, just so you know, integrating a cosecant is, of the 20 antiderivative formulas that we're going to have at the end of today, that's probably the least common one. But the fact is, if it did come up, you'd want to be able to answer the question.
Would you ever, is it better to leave it as that form, or is it, would some textbooks or answers have like hidden sign and cosine?
Well, this is the first thing we came up with.
Right.
And we just proved algebraically, forget calculus, algebraically this is equal to this. This is the version everyone uses for the simple reason that the negative sign is the thing that will always be left out. It will always be forgotten, and which will then change my answer. We don't like a negative in front of a log because we have several antiderivatives that have logs in them, and none of them have negatives, if we can avoid it. Sines and cosines, they're negatives, right? Trig functions in general have negatives. But logarithms, we don't want to see negatives. Again, because it's too much to remember. So this one is the most obscure probably of all of them, but we've got it. That's kind of cool. So now let's throw in the potential that we might have to do a substitution. All right, so here's what I got. I got the integral of the secant of e to the negative x over e to the x dx. Now, you have antiderivative formulas. We have just derived antiderivative formulas for the secant, the cosecant, the tangent, and the cotangent. You never have to re-derive them. Use the results. They're on your sheet that has all the integration formulas on them. I only need you to use the results. I'm doing the derivation so you see where they came from. I don't say this jokingly. In a business calculus class, I've taught business calculus, there's no derivation. They avoid the word limit like the plague. So here's the functions, here's the derivatives. Here's the functions, here's the antiderivatives. Any questions? Good. There's no derivation. You are simply given every formula and asked to memorize. Is there any understanding of what it is you're doing? Well, my experience is none. Now, STEM people can't take business calculus. They have to, because you have to understand where everything came from. Why? Because you're also going to do this stuff in physics. You can't just memorize formulas. You have to understand things. I want to do this. I'm not worried about the secant. I'm worried about the argument. I only have one choice of my substitution, and it's what?
E to the negative x.
E to the negative x. So then what's my du?
Negative e to the negative x.
Oh boy, if only I had one. Oh, wait a minute. That e to the x lives on the bottom, doesn't it?
Mm-hmm.
True or false? True. True. I need it to be a negative. So far, so good? Can I say this is now negative secant u du?
Mm-hmm.
Now we got to go through and re-derive the entire antiderivative formula, right? No, we already did. The next thing you write should be the antiderivative. There's no algebra to perform. We did it. That's what all of that was for. So that you can now fast forward to the end. So this is what? Negative log
Secant x plus tan x.
Absolute value, don't forget the absolute value
Yeah.
of secant u plus tan u. I haven't substituted back yet. You with me so far? Now we'll I'm sorry, I'm not negative, my bad, sorry. And now we'll have log of secant e to the negative x plus tan e to the negative x. Is there anything I can do to this? Is there any algebra I can manipulate this with? Is there any simplification? I asked you this question last day, and a lot of times we get in trouble because the rules of logs, not everybody's totally comfortable with. It out loud. The log of a product is the sum of the logs. The log of the quotient is the difference of the logs. But the log of a sum or the log of a difference doesn't have any simplification. It doesn't go in reverse. And that's where we sometimes get in trouble. So can I do anything with that? For a lot of us, the correct answer is, I'm not sure. Am I right? I'm not sure. So therefore, what should I do? Nothing. Because if I do something, it might be the wrong thing. I'll give you a hint. You can't do anything. So if I do something going forward, it'll be the incorrect thing. That is actually as far as it can go. But if I'm not sure, better to leave it alone than to write something that's not true.
So what happened to the negative?
Did I? Oh, I'm sorry. That's why. Yeah, you're right, Chase. I had it and I couldn't figure out. I couldn't read my equal signs. You're right. That should be a negative still. Now, that's ugly. But it doesn't matter because at the very worst, I'm going to evaluate this at different constants using a calculator. That's the worst thing that's going to happen. So I'm not worried about that part. I'm worried about getting the correct antiderivative. Yeah, it has a negative. I just couldn't see it. Okay? So that's as bad as it gets. That's not very fun, but it is what it is. So we now have antiderivative formulas for all 6 trig functions. So our list of antiderivatives is now 10 of them involving trig. Because we have the original 6. So in other words, we have the antiderivative of secant squared, of cosecant squared, of secant tangent, cosecant cotangent. But now we've added all of these. So we now have 10 antiderivative formulas that are just straight up from trig functions. Right? We have the u to the n, we have the different logs, we have all those things. We still have 2 left to look at. One are the hyperbolics, which are actually some of the easiest ones, believe it or not. And the most complicated of them all, probably, the inverse trigs.
For the exam, are we allowed to integrate by sites in a way, like just skipping stuff?
Well, it depends it depends. That's the right question, but it depends. If we're doing a problem, like I wouldn't skip steps here. I would definitely rewrite this just because there's too many things that can go wrong. But I did mention to you, we did all this kind of stuff today in my Calc 3 class, but in a higher level. And I would write down, here's the difference in the higher levels. I would write this down, but they were able to go from here to here. In other words, they could physically not rewrite the problem if they chose to. But they had to do this, otherwise they're not going to be able to set it up. There will be a point when you're saying, okay, this is just secant u du, my antiderivative is secant u tan u. There's a point, and I'm going to want you to reach that point, but not today. It's too soon. You want to do this enough times because you said, if I can just see it, can I just do it? Yes, but most people can't just see it yet. You've got to do enough problems. Why? Because we have 20 different antiderivative formulas, and all of them are different in terms of the substitution. So you actually have to be really comfortable on all of them. But there's a point when I want you to be able to skip the physical rewrite of the problem. But don't skip it yet. I don't need you there yet. Yeah, exactly.
Why are you allowed to keep the negative in front of the log in that answer?
Well, because this answer here, this guy right here this whole thing here can be negative.
Oh, okay.
The whole answer can be negative in this case. It was very specifically the log of the secant.
Okay.
Because if you remember, a secant, remember, a sine and cosine return numbers between -1 and 1. Secant returns numbers outside that range. So from 1 to infinity and from -1 to infinity. And now I'm taking the absolute value of that number. So it's always bigger than 1. Does that make sense? That's why for the secant specifically, it was always positive. Not true for the rest of them. I can come up with things, think of it in the sense of I could have situations here where both of these are very, very small, and then the log of that might be I'm taking the log of a really small number, that's negative. But if both of these are somewhat large, what they're usually going to be, now I'm taking the log of a number bigger than 1, so this part's positive, so my final answer is negative. So it's going to be 50-50. It was the very specific case. So when I said I don't like a negative in terms for my antiderivative formula, if the final answer to a question is negative, it's negative. You don't worry about that. And how often will your final answer be negative? About
Half the time.
About half the time, yeah. It's if my situation I said before is if the final answer is always positive, you don't express it as the negative of a negative. But if this answer is actually negative half the time and positive half the time, then the negative in front isn't going to cause a problem. Again, these are all great questions you guys are asking today. Where did we go? There it is. Okay, let's do one more of this nature. Let's do, how about x squared tangent of 4x cubed dx? Because generally speaking, your arguments are never going to be just an x. They're almost always going to be a function. Almost always. So let u equal what?
4x cubed.
And then du is
12x squared.
12x squared dx. I am not worried about the 12, I'm worried about the x squared. Do I have x squared in my integrand?
You do.
I do. You found it. It was carefully hidden. So what am I going to do? 12, 1/12. Now I have exactly, and there's no exception. I have to have exactly the chain rule factor down to the coefficient in order to pull off the substitution. But if I only lack the coefficient, that's easy to fix. But if I lack the exponent, I cannot fix that one. That's a completely different problem. I say it kind of half tongue-in-cheek, but every time you run into a problem where you're saying, I can't do this by u sub, that means it was probably a Calc 2 problem. Change that first exponent to any real number other than 2. It's a Calc 2 problem. We don't know how to do that one because it's not a u sub. But because this exponent was exactly 1 less than this one, I could do it as a simple u sub. So when I rewrite this one, I'm going to rewrite it as 1/12 10u du. So that's 1/12 of what?
Natural log of absolute value of secant u plus u.
And then that will be secant of 4x cubed. Now, there's no place else to go. I'm done. Question. Would it be legal to take this 1/12 and move it up as an exponent for the secant function? Is that legal?
Mm-hmm.
Is it advised?
Yeah.
I don't think I want to do that because if I had to evaluate this, you really want to take a quantity inside a log, raising it to the 1/12 power. It's correct. I don't think it's a better answer at all. In fact, remember we said go the other way. Whenever you have log of something to a power, always pull the power in front. So why would I want to take the power and put it back as an exponent? That just makes it ugly. No, I would leave it like this. Absolutely leave it like this. Okay? Questions? Okay. Now we're going to move on to the inverse trig. Of all of the functions that you integrate or differentiate, x to a power or u to a power, and the natural log of x or the natural log of u are probably 1 and 2 in terms of commonality importance. Next is probably exponentials, sines and cosines, they kind of go together. And then believe it or not, probably the next one is inverse tan. Inverse tan is actually usually considered top 5 or top 6 in terms of how common it shows up. So an antiderivative involving inverse tan turns out to be one of our more important formulas that we need to derive. So let's remind ourselves. If I said, what is the derivative of the inverse tan of x? If you don't know it, again, have that formula sheet sitting right by your side. What is this?
1 over 1 plus u squared.
Well, for now, it's just x squared.
Yeah, x squared.
Yeah, I'm doing an x first. We'll get to the u in a minute. In fact, while we're at it, Chase, let's just go ahead and do the u. So now if I said I have u of x, Now it's 1 over 1 plus u squared, and then the
dx.
chain rule factor. Great. That's probably the majority of the time. But now I need to establish an antiderivative formula. So I'm not going to start with the substitution. I'm going to start with the first one. Do we all agree that that's probably the best answer? Life is good. Life was easy. And you're rarely going to see it in this form. Well, you know, but I know how to do a u sub now. I know how to attack that one. That's not what I'm talking about. Here's the form that we need. This is the form you're going to see most often. Assume A is not 1. Maybe that's a 4, maybe that's a 9, maybe that's a 16. Heck, maybe that's a 7. It's something yucky. What if it's in the form of a squared plus x squared where that a is not a 1? Do you think that this has potential to be an inverse tangent somehow or another just because of the form of that denominator? It would make sense, wouldn't it? So what we're going to do is manipulate this algebraically to figure out where to go. We want to do the substitution, we want to do the u version, but we need to do the x version first. Because the most common versions of all three, right, all three of my inverse trigs, right, inverse sine has square root of 1 minus x squared. Inverse secant has an x squared minus 1 in the denominator. What if it's not a 1 in my antiderivative? What if it's something else? Well, it's still going to be one of those forms, but it's a bit more complicated. So here's what I want to do off to the side. I want to take a squared plus x squared, and I want you to factor out the a squared. Can you do that? What happens if I factor out the a squared? What will I get?
1 plus x squared.
Plus x squared over a squared.
The x squared over a squared. I'll put it in front like that. Do you agree?
Yeah.
How about that? Is that true?
Yeah.
Seems kind of weird. Why would I do something like that? Because I need to make this guy look like this guy. So, based on what I just said there, can I write this as 1 over a squared times 1 plus 1 over a times x quantity squared? Are these the exact same? Well, if I distribute, yeah, I think these are exactly the same. Okay, so far so good. What do I do? This is just in the way. What do you do with coefficients that are in the way in integrals? What have we done so far with them? Last day. It's a coefficient that's in the way.
Oh,
Yeah, get it out of there. Pull in front. How's it going to show up? Numerator or denominator? Well, it lives in the denominator, so that?
Mhm.
Would you agree this one here looks a heck of a lot more like this one? It's 1 plus something squared. It's a lot more like it, isn't it? It's 1 plus something squared, but it's not 1 plus x squared. It's 1 plus thing squared. Do you see a substitution?
Substitute x over a.
Yeah, make that your u. Exactly. So if I said, let's let u equal 1 over a times x, then what's du? This is why you don't write as a quotient, because you're not using quotient rule. Your du is just 1 over a. Oh. So for me to finish this off, I need a 1 over a in front of the dx, don't I? All right. I need to do this. But if I do that, then what should I put on the outside?
No.
An a. We're almost there. Let's make this prettier, shall we? I know this is pretty, but let's make it prettier. Right now in front I have 1 over a. Here I have 1 plus, or 1 over 1 plus u squared du. Ooh. Can we integrate that now?
Mhm.
Yes, we have 1 over 1 plus u squared du. We can integrate that. And what will the antiderivative of this part be? Won't that just be inverse tan of u?
Mhm.
That's not going anywhere. I need that guy. Now let's substitute back. And there's my antiderivative. Whoa. We said we thought it should look like an inverse tan, but it's not just inverse tan x. We had to manipulate it. We had to tweak it. Wow. I said algebraically this was going to be a little bit busy. That's very busy, wouldn't you say? Let's do an example or two just to make sure we understand what we just said. I'm hoping that absolutely nobody ever has an issue with this. At any level, nobody generally has an issue with that. That's not the problem. Here's the problem. I want you to integrate 1 over 16 plus x squared dx. The next thing you write should be the final answer. There is no substitution. Why? My argument is just an x. It's just that my constant isn't a 1. Now, here's the one thing I need you to train yourself, because we are going to do a ton of problems over the next several weeks where you're going to have things involving sums of squares, things involving difference of squares. Things like, a squared plus x squared, a squared minus x squared, blah, 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 blah. You don't see a 16. What do you see? Look at the form. You don't see 16, you see
4 squared.
4 squared. Anytime you have a sum or a difference of squares involving numbers, it's not the 16. 16 doesn't show up anywhere in the answer. The 4 shows up in my answer. So the only thing I'm going to write down, I'm going to go like this. To make sure that I don't somehow treat it as a 16, can I write the answer as the next thing? Yeah, I just derived the formula for it. The antiderivative of, where is it? The antiderivative of this is this. So once I identified what's being squared, or I'll do my part. There.
1/4.
1/4.
And then 1/4 times x.
1/4 x. I'm done. That's it. You like that? You don't ever re-derive things once we derive them, but there's no way in the world we would have seen that was the tweakage we needed to perform. So, assuming that the majority of time, and I mean the majority of time, at least 99% of the time when you're doing an inverse tan, it's not going to be a 1. But it doesn't make it hard. I just have to look at it and see it for what it is. What if that number is not a perfect square? Oh my gosh. That's impossible, right?
1 over root 13.
Oh, that really wasn't hard at all, was it? The question is what is being squared. In this case, it would be root 13, and then that's what shows up in my answer. That's it. I can put any positive number here, and you're writing the answer as the next thing. You should like that. That's minimal work. Now let's do one involving chain rule. Because the most of the time, again, you're still going to have to do your substitutions, but that gets a little bit busier. Let's see. Oh my goodness, that looks impossible, doesn't it? Is the derivative, is the numerator the derivative of the denominator in this case? Because, by the way, whenever you have a quotient, that really should be the first thing you look for. The derivative of the denominator would still involve in either the 2x, wouldn't it? So this is not a log problem. Boy, that denominator looks so complicated.
Ah, that's fine. Yeah, that. It's
That's e to the x quantity squared, isn't it? So this is a squared plus u squared. And as long as I have the derivative of u in my numerator, I'm good. So let's, do you agree that that's what I want? Not e to the 2x, no, I want e to the x. Then my du is e to the x dx. So that means this is of the form 1 over 6 squared plus u squared du. Again, I need the u squared in the denominator so I can use the inverse tan formula. That's why our u is e to the x and not e to the 2x. Now stare at this for a minute. Well, that was the easy one. This is e to the x quantity squared. That's my substitution choice. And then I have exactly the chain rule factor that I need in the numerator. Can you write the antiderivative of this as the next thing?
Yeah.
Yes, and you have to. There's no work to do in between. This is now a straight up formula. 1/6 inverse tan of what?
1/6 u.
1/6 u. Now I will substitute back. Whoa. That wasn't that hard. The hardest part was recognizing the form. Now, this is what calculus will become. Your last exam, you're going to have a lot of integration problems. This is going to be mostly integration. And I'm going to have a whole sheet of integrals. And if you haven't practiced, you might have 10 different problems, but you're looking at them going, they all look like the same problem to me. They won't be. But if I'm not familiar with what's involved, I can easily see them as the same. We did a problem last day, if you remember. I did the square root of x minus 2, then I did the square root of x squared minus 2 times x, then I did the square root of x minus 2 times another x. And they all kind of looked the same, and we realized there were 3 very different problems, and I had to set them up differently. Well, what if, and I'm notorious for doing this on exams. Oh, it's my favorite thing to do on exams. These will be consecutive questions on the exam. If I ask these two, which I will, they will be right in a row. Did I just ask you the exact same question twice? No, they're quite different. It's not about memorizing. It's about seeing something and knowing exactly what category it falls into. These are very different. Tell me about the first one. I don't want to know what's the answer. Tell me what you notice very distinctly about the first one.
It looks like the derivative.
The degree difference is exactly 1, which means the numerator could potentially be the derivative of the denominator. If my denominator is the u, by the way, this problem we did last day. The entire denominator is the u, then what's the du?
4x cubed dx.
You just put 1 outside here.
Tell me about the form of my answer. It's going to be a
1 over
log. This is 1 over u du. My answer is going to be a logarithm. Do you agree? Everyone see that? This is of the form. I'll write it. I'll squish it in. This is 1/4 1 over u du. My answer is natural log of what that denominator looks like. There is a priority whenever you have a quotient, particularly rational functions. Look at the degree first. If the degree of the numerator is exactly 1 less than the degree of the denominator, then there's a very, very good chance that it's the derivative over the original function, which means it's a log. That's one of the easier ones at this point. My numerator is not the derivative of my denominator, is it?
Are we going to be rewriting the denominator as 5 squared plus x squared squared?
We will now. We weren't going to here, though.
Yeah.
So this is what I want you to see. When you see this problem, I'm hoping you see the degree difference first.
Mm-hmm.
So that means my numerator could be the derivative of the denominator. We checked it. It is logarithm. I'm happy. I'm done. It's not the case here. So now Chase says the next thing we're looking at is, can I see my denominator as a sum of squares? That's the next thing. By the way, that's the only other thing it can be. If I see my denominator as the sum of squares, what am I seeing this as?
X squared squared.
Now, is my numerator potentially the derivative of the x squared?
Mhm.
Yes. So that means this is going to be inverse tan. But would you say the difference between these two problems is very subtle? I mean, you should say that. Now, I could make the numerator any degree on planet Earth. But if I made it any other degree, we can't use any Calc 1. It's not a Calc 1 problem. This is a Calc 1 problem because it's derivative over function logarithm. This is of the form a squared plus u squared, and there's my derivative of u on top, inverse tan. I will want to finish the problem, obviously. But I want you to see that when you are looking at the problem, you have to categorize it. Which type is it? The moment you recognize, oh, this is a derivative of, boom, this is going to be a log, I will probably get it correct because I know what type it is. But if I'm looking at them and I don't see them as different problems, is it likely I give essentially the same answer to both? Yeah, then I know one was wrong. That's called hedging your bets. Not a good idea on a math test. That's kind of like saying, well, I have a whole bunch of true-false questions, and I know from history this instructor likes asking just as many trues as false. So I'll answer all of them true, and then I know I'll get half of them right. Wow, that's not a very good strategy, is it? I'd rather get them all right. But the idea is, if I don't recognize a difference, I'm very likely to do both the exact same way, and that's not what I want to do. So inverse tan is very specific. My denominator has to be in the form of a sum of squares. And then once I recognize what's being squared, I'm looking for that derivative on top. That's the key. You all with me on that? Kind of crazy. So that's inverse tan. This one's fairly common, but we like inverse tan because there's no roots. Inverse sine and inverse secant have roots. They can get a little bit more icky, okay? So let's remind ourselves. Okay, we'll start with just this. I'll do my part. Okay.
Root 1 minus u squared.
1 minus, well in this case, x
Oh
squared.
yeah, x squared.
Now let's do the general. All right, that's the most common. So now for the antiderivative, let's start simple. If I have something of this form, I know the answer is inverse sine x plus c. Beautiful. And I said that's not the form you're usually going to see. The form you're usually going to see is going to look like what? A squared. Now, do you remember the algebra we did a moment ago to complete the inverse tan? We factored things out, we manipulated it. What we did was we eventually made this look like 1 minus u squared. We're going to do the exact same thing. We're going to make that denominator look like 1 minus u squared. So we're going to do all of that off to the side. Because if I can do that, then I can complete this answer fairly soon. All right, so off to the side. If I started with a squared minus x squared, and I want to factor out the a squared, what does that mean? We did this just a moment ago.
1 minus 1 over a squared times x squared.
Okay, so far so good? Okay, one more thing. Oh. Can I pull that out of the root? Yeah, I want to pull that out of the root. So how will that come out? It'll just be an a, won't it? And I'm going to write this as 1 over a times x. Now, the moment I wrote it that way, do you kind of see where the u is going to come from? Mm-hmm. It's going to, hopefully it's just like the last problem. It should be obvious, okay, the 1 over a times x is going to become my u. Then I'm going to have a 1 minus u squared. That's a good thing. But I got that a in front. I don't really know what to do with that yet. Okay, but we'll figure it out. So here's what I want to do. I now know this is, in fact, you know what I'm gonna do with that? I'm gonna take that 1 over a and I'm gonna pull it completely out of the integral. I don't want it in the way. I don't want to be confused. A lot of times when we have a coefficient, which doesn't affect our answer, it's just I multiply it by the coefficient. But when we have a coefficient in the integrand, our eyes sometimes are drawn to the coefficient, which doesn't have anything to do with my integration technique. I'm not looking at the 1 over a, so let me pull it out of the problem completely and only write what's left over, which would be 1 minus 1 over ax quantity squared under the square root. So do we agree that these are exactly the same? Because if I multiplied this back in, I'd have to multiply it as the square root of a squared, and then everything works nice. So clearly, I want to have my u equal what? Just like before. This?
Mm-hmm.
Then my du is 1 over a
Yeah.
dx, okay. I don't have a 1 over a, well actually I do. It's right here. Oh, can I just do that?
Mm-hmm.
Everyone, can I just bring that? Wow, this is really clean. That means what I have now, this is of the form 1 over 1 minus u squared du, because there's my du. Because I can't see the 1 very easily. That's pretty clean. I don't even have any 1 over a's. I just have that. That's kind of nice. What is the antiderivative of this guy? Well,
Sine
over
negative
there.
1u.
So inverse sine of just u. Now let's substitute back. This wasn't that bad. And I don't even have a number in front, do I? Cool. All right, let's do a simple one to start with. My argument is just an x. The question is, can I write the answer as the next thing without doing any work? Yes, in fact, you need to write the answer as the next thing because there isn't any work. Well, there's one thing that I might be wise to do. I will always do that. What is the error that I'm likely to make if I don't do that?
If it 1 over 9.
I'm gonna have 1 over 9 in my answer. Would anybody do that? I'll give you a hint. Almost 100% of the time when people don't do this, they use the other number. You had the right idea, but you went too fast. There's no 9 in my answer because 9 is 3 squared and only the 3 shows up. So I think it's really wise. Always do that. Just, it's insurance. So can I write my answer? Well, it's inverse sine of a third x plus c. Now what? Now what?
That's it.
Am I done? Oh, I'm done. There's no 1/3 in front, is there? That was inverse tan. That's not inverse sine. So sometimes we make a mistake by employing a different formula. That was pretty clean, wasn't it? I mean, that was really not bad at all. So let's do one involving substitution, involving chain rule. Every one of these formulas is on that formula sheet, the completed form. What's not on the sheet is the derivations. So you see where things came from. The things that we're doing right now, me factoring out the a squared, all that kind of stuff, this becomes extremely common next semester when you're doing problems. This type of algebraic approach we do all the time when we get our more complicated integrations. We manipulate things algebraically before we apply the calculus to make them look the way we need them to look in order to finish the problems. So let's do another one of this nature. Let's say we have 64 minus x to the 6th, and on top I have 4x squared dx. Now, look at this, the whole thing. If that were my u, then I would need an x to what power on top, if that whole thing was my u? I would need an x to the 5th on top. If I had an x to the 5th on top, then this would just be u to the negative 1/2 du. That's straight up, fast, easy. The degree difference is not 1, therefore this can't be my u. That's, by the way, that's always your first choice because that's the more common one. Again, when I have things of a polynomial nature, I'm looking at the numerator to see is the degree difference 1. The degree difference is not 1. So now I look at my denominator and saying, it looks like a difference of squares. What is actually being squared?
So it's going to be 8 squared minus x cubed squared.
Now,
Now
the
it's a
degree
1.
difference is exactly 1. So clearly x cubed is my u, and there's my du on top. That's a good thing. That means it's going to be inverse sine. If this is a 7 or a 1 or a 10, I can't do it. I need it to be exactly 1 less than this one to complete this. Okay? The nice thing about every Calc 1 class ever given in the history of the world, it always works. In Calc 2, it never works because you're learning different things. In Calc 1, you're always going to be able to integrate it. The textbooks never give you problems that you can't. And if they did, it's probably a typo. Right? So, something evil. Right? You came up with like one of the most evil typos I've ever seen. And even the solution ignored the typo and gave the answer to a different question. So in this case, I'm going to say, let's let u equal what?
X cubed.
X cubed, not the whole denominator, just the x cubed. Then my du is 3x squared dx. All right, I have a 4. Do I have to figure out in my head what fraction to introduce? And no. What did I do last time?
5 by 4.
No, not divide, take it out.
Oh, yeah.
Now what do I need to be there?
3. So
There. 4/3 times 3, that's my original 4. Do it that way and you're never going to mess up your coefficient. So when I do my substitution, this will now look like 4/3, 1 over 8 squared minus u squared under the root du. Because this is my du right there. Can I give you the antiderivative as the next thing? Yes. It's 4/3 inverse sine of 1/8 u. Let's see. And now I substitute back, but only now. 4/3 inverse sine of 1/8 x to the 3rd power. That's it. How would I check this answer? This is a perfect opportunity. We haven't done this yet. How would I check this? I take its derivative. Okay. Let's check it. I'm a little squeamish. I want to check the answer. So when I take the derivative, it's going to be 1 over 1 minus, I'm sorry. I need the 4/3 out in front. Sorry. 4/3 times 1 over 1 minus 1/8 x cubed quantity squared under the square root times the derivative, which would be 3/8 x. And now I got to simplify this and manipulate the fractions under it. This is correct. You agree? This is going to take longer than the original problem, just so you know. There's going to be more steps. Might we make a mistake checking this? I got to square that, then I get a common denominator, then get the denominator out of the problem because there's no quotient in my question. This is correct, but it's going to take us a while. Might we make an error on this one? Oh, yes. This is where I said you want to use technology. This is where I'm serious. We've been practicing derivatives. We've been doing derivatives all along. But now we're higher level now. We're doing integrations. This is last test. I would go to Wolfram and say, what's the derivative of this? And it better give me exactly this verbatim. It's already simplified and done everything. Because this problem is not about your ability to differentiate. This problem is about your ability to integrate. Right? Now, do we have derivatives on this? Yeah, of course. But the idea being, in this case, the check might take longer than the integration. And the algebra on the check is way worse than the algebra on the integration. In fact, was there any algebra on the integration? No, just recognizing what was being squared was the only algebra. The algebra this way was easy. The algebra this way is kind of nasty. Okay? So that's one where I might use something else to take the derivative to check that I did it right. Because all I got to do is make sure I get the integrand back again. You with me? This will be a good stopping point. We still have more to do. All right, so we've introduced integrals that get us back to inverse tan, get us back to inverse sine. So obviously the last one would be get us back to inverse secant. So let's remind ourselves, an inverse secant, it's not ridiculously common, but it might be the most interesting one because it has properties that the other ones don't have. We'll remind ourselves. Now, inverse sine, I have a 1 minus x squared. Inverse secant has an x squared minus 1. That cannot be commuted. That's a subtraction. So those formulas are very different. The derivative of inverse secant involves absolute value. The antiderivative does not have to involve absolute value. So in reverse, if I integrate anything of this form, I know I get inverse secant. Okay? Piece of cake. So just like the last few examples, what if that 1, are we sending?
Yeah.
Okay, what if that 1 is not a 1? It's a 4, it's a 9, or even worse, it's an 11. It's something squared. Well, our next goal then, just like before, would be to get something in this form. If I can figure out this, then I can do my chain rule, I can substitute. But I gotta get this first. Again, the most common problems you're gonna see with inverse trig functions are not necessarily gonna involve ones. They're gonna involve any number. We're not restricted in that sense. So, like we did before, let's start with x squared minus a squared, and now let's factor out an a squared. Is that a conversation? Or?
Somebody's on their laptop.
Outside.
Somebody want to close that? Is that if that's distracting to you? Okay, so if I factor out the a squared, just like before, except this one, it comes first this time. Thank you. Okay, so far so good? Again, we see the 1 over a times x, hint, hint, hint. That's where my substitution is going to come from. But I got a lot of other stuff going on. You see, I got an x in front also, which is going to be kind of tricky to deal with. But let's start with this right here. Now if I put a square root on this, that gets a square root. So now that a will come out. Okay, so let's write that. So then finally, if I have 1 over x square root of x squared minus a squared, we know that's going to be 1 over x times a times all of this stuff. Now, when I do this integration, like before, clearly my u has got to come from here, right? My u's got to be the 1 over a. So, as I just keep adding the pieces after the fact here. So we would say, let u equal 1 over a times x, du is 1 over a dx, just like every other time. Well, I don't have a 1 over a on the outside, or do I? Yeah, I actually got it right here, don't I? Does everyone see right here, I actually have a 1 over a. That's a good thing, right? So can I take that one and put it right here?
Yes.
Beautiful. So when I make my substitution, does everyone see this is going to be my du and this is going to be u squared minus 1? There's just one really small problem. That's u squared minus 1 and that's du. Does everybody see something kind of
Still
hanging
next.
around?
Yes.
What do I do with that guy?
Absolute fine.
Well, no. I'm about to replace my variables and have a u and a du. Can't have an x at the same time. There is no possibility in any context where you can ever have an x and a u in the same integral at the same time. If you do that, doesn't matter what you write afterwards, it's completely wrong because you just made them both independent variables and all hell breaks loose. I mean, talk about dogs sleeping with cats. At that point, you think the cats are eating the dogs. Kind of crazy. Nope. No, I gotta do something with that x. Yikes. Oh, wait a minute. We know what to do. If u equals 1 over a times x, what does x equal?
1 over a times u.
Oh, so when I substitute and replace everything else, can I just make that an a times u?
Yeah.
Yeah, kind of what I need to do. So, here's what I got so far. A times u. Square root of u squared minus 1 du. Beautiful. I still don't like that a there. But can I take this and move it outside as a 1 over a? It's in the denominator. So can I move it out here?
Mhm.
It's exactly the form I need it to be in. Okay, it's exactly the form that I can now tell you the antiderivative. So the antiderivative of this is going to be what? Inverse secant of u,
Times 1 over a.
the 1 over a. How interesting. Inverse tan had the 1 over a. Inverse secant had the 1 over a. Inverse sine does not. Do you see that potentially as a problem in the future? 2 of the 3 got a 1 over a? Yeah. That's a common mistake people make as they forget and they put a 1 over a in front of all of them. Inverse tan and inverse secant both get the 1 over a. Inverse sine does not. So if you look at the formulas, you'll notice the inverse sine doesn't get the 1 over a in front, but the other 2 do. Well, that's not bad. That actually worked out kind of nice. So after all is said and done, we're seeing this common theme of the 1 over a. Okay, so that is not the worst thing in the world. We can live with this. Right? We're okay with this. Now, let me remind you of something we did. Okay. I want to take this derivative. And this, by the way, this is an exam question, because we're already doing this on the exam, as you know. Yeah, Cece.
How come, I was supposed to ask this a lot, but how come, we're using secant?
It's inverse secant.
Oh,
Inverse. These are inverse. This is not sine cosine.
no, I mean, well, like, how come there's no inverse secant?
There is, hold that thought for a
Oh,
minute.
cosine, sorry.
Hold that thought for just a moment. I'll explain why that in a moment. You'll go, oh, okay. It's kind of it's a real simple reason. We only need the sine, tangent, and secant inverses, not the cosine, cotangent, cosecant inverses. And there's a really simple reason, but hold off on that. So what is this? Well, let's see. I know it's 1 over absolute value of e to the x. I know it's e to the x quantity squared minus 1. And then it's times the derivative of e to the x, which is the derivative of e to the x, which is e to the x. Is the absolute value of e to the x just e to the x?
Yes.
Can e to the x ever be negative?
No.
No. So can I go like this?
Yes.
I can't cancel if that thing can be negative, but e to the x is always above the x-axis. It's strictly positive. So my final answer is 1 over e to the 2x minus 1 under the root. This answer does not look like that anymore because I canceled something. Inverse secant is the only one of these where when I'm all done with the problem, it is common, not always, but it is common that the chain rule factor on top canceled with something on the bottom. It's actually very, very common. I no longer see, this doesn't look like an inverse secant anymore, does it? Or derivative, because I don't have anything over here. So I keep this in mind. Inverse secant, therefore, can be one of the trickier ones to anti-differentiate. Okay, so let's do an example. I have the antiderivative of, how about x times x to the 6th power, in fact, let's make that minus 16. Now, I have no idea what the antiderivative of this is, but what form does it look the most like of all the things you've learned so far? Kind of an OW. We just do. Looks like an inverse secant. Okay. Is it safe to say, by the way, I have nothing on top, so there's no, let the bottom be u, let the top be du. No. So I'm looking for a difference of squares, probably. Everybody cool with that? So I'm thinking that that's where we're going to go with this. What's the problem? In inverse secant, hasn't this got to be the same variable? I have x squared and I have x. Here I have x to the 6th and I have x. Oh, but it's x cubed squared. And I still have x. What do I kind of need this to be?
That'd be x squared.
Doesn't this really need to be x cubed? In other words, it needs to be the same thing.
Hmm.
If I'm doing my u sub here, that's why I said this one is the trickiest one of all. Do we agree that we would let u equal x cubed? And then du would be 3x squared dx. Do we agree with that? That's what I need. I don't have 3x squared on top, and I definitely don't have x cubed right here, because I'm going to make a u substitution. That's u squared minus 4 squared. But that has to be u also, and it isn't. Oh, darn. Ah, man. If only that was an x cubed and I had an x squared on top. Any ideas coming to mind?
Multiply by x squared over x squared.
Ooh, you ever hear that? I need an x squared on top and I need an x cubed on the bottom. But if I multiply top and bottom both by x squared, I would accomplish both of those. Is that legal?
Yep.
You can never multiply or divide by anything that could potentially be 0. Can x be 0? X to the 6 minus 16? Can x be 0? No, x can't be 0, can it? Because then it'd be imaginary. So that's totally legal. In fact, it's the only route. That's where 200 pounds is. That was good. That was really. Did I tell you that ahead of time, or did you? You just figured that one out. No, that was beautiful. This is the only way I can do the problem. Do you remember the previous example when we were all done, we canceled the e to the x's? Well, if this was my answer, wouldn't you cancel the x squares naturally? But now I'm going backwards. I need an x squared here, but I need an x cubed here. But I don't just need an x squared, I need a 3x squared. So what if I put that 3 there, but I put the other 3 out here? You didn't know I was as clever, did you? Now, I'm going to rewrite this as is. So now I have x cubed. I have x cubed squared minus 4 squared. I have 3x squared, I have dx. Algebraically, this and the original problem are absolutely identical. But now I have everything that I need in order to do my substitution. So when I do my substitution, there's my du right there. So this is 1 over u, the square root of u squared minus 4 squared. Try to make u and 4 look different. You all see it? Can I write the antiderivative as the next thing without doing anything in between?
Mm-hmm.
Yes, and that's what I want to do. So the antiderivative would be the inverse secant of 1/4 u. Does the 1/4 show up in front on this case?
Yes.
Does this guy get the 1/4?
Yes.
Yes. And I already had a 1/3,
1/12.
so therefore it's a 1/12. I am completely finished with the calculus. We will substitute back. Here's what made this one tricky. If I asked you to differentiate this, you would have taken the derivative of this on top, you would have had an x squared. Then you would have put this next to the square root on the bottom with an x cubed, and everybody in the room would have then canceled x squares, wouldn't you? And so you would have ended up with something that looked like this guy. But that's not the form of inverse secant. We had to multiply top and bottom. Inverse secant is the only one of the derivatives that you regularly cancel. So when I'm doing an antiderivative, I may have to multiply numerator and denominator before I start. It's the only one that you have to do that with commonly. Okay? That's why I said it's probably the trickiest one of all. Is it real common? No. but it does come up, okay? Now, we're gonna finish off this with probably the least work of all, and that's, believe it or not, the hyperbolics. So, we did in class, we did the hyperbolic cosine of x, and we got the hyperbolic sine of x. We differentiated the hyperbolic sine of x, and we got the hyperbolic cosine of x. And the only other one we ever actually do, by the way, the only other one is the hyperbolic tangent. And we get the, we never deal with the hyperbolic cosecants or cotangent. They just never come up. I've never actually seen them in any context. Not that they don't exist, but it's not worth wasting any time over. Okay? So that's true. Then integrals going the other way are a piece of cake. I don't have to change these to exponential. The exception, if you remember, only when the argument is a natural log. So if it's hyperbolic sine or cosine of natural log, that was the only time you change it to exponential, because then you have e to the log and everything undoes and you get something really nice and simple. But the rest of the time you just leave it alone. So I want to integrate, let's say. How about I want to integrate something of this form? The hyperbolic sine of 1 plus the hyperbolic cosine of x. I like stuff like this. Love questions like this. How would I do this?
Well, the numerator looks like a derivative of the denominator.
Beautiful. The numerator looks like the derivative of the denominator, does it? I'm going to write it out formally. Let u equal 1 plus the hyperbolic cosine of x. Then what's du?
Sine hyperbolic x dx.
There is no plus or minus with the hyperbolics that you got to worry about in this case. Oh, so that means this became 1 over u du? Is it actually that easy? Now, hyperbolic cosine essentially is the average of e to the x and e to the negative x, both of which are always positive. So can the hyperbolic cosine ever be negative?
No.
No. 1 plus the hyperbolic cosine definitely can't be negative. In my final answer, do I need the absolute value?
No.
No. Would it be okay to leave it though if I wasn't sure?
Yes.
Yes. I would say absolutely, but that sounds like a bad thing. If you're not sure, leave it. If you know that 1 plus hyperbolic cosine is always positive, in fact, it's always bigger than 2, because hyperbolic cosine never is smaller than 1. Okay, beautiful. Now, brand new question, completely unrelated in every conceivable capacity to that question. Are these the same questions?
No.
At first glance, they kind of look the same, but they are not the same questions. The denominator here looks like a sum of squares.
A tan inverse.
What is my u going to be? By the way, it helps you. That's literally, that is 1 squared.
Cosine.
Let u equal, how about just the hyperbolic cosine? Then du is the hyperbolic sine. In other words, this is 1 squared plus hyperbolic cosine squared, if it helps you think of it that way. So therefore, with this substitution, it's 1 over 1 plus u squared du. And that is, what, Chase?
Tan inverse.
Inverse tan of u. I don't have any fractions to worry about because it's a 1. So that's inverse tan of the hyperbolic cosine. Whoa. Now, we have trig identities, and we've used some today. We used some Pythagorean identities today. Are there any Pythagorean identities involving the hyperbolics? We did go over this way back when, and it's on your sheet. It's not the sum of the squares that equaled 1. Do you remember?
It's the difference.
It's the difference. This is actually called hyperbolic geometry in the highest levels. I think I've made reference to this. Did I talk about why E equals MC squared? Did I talk about that book with you guys?
Yes.
And it's fourth dimensional non-Euclidean geometry where they're using hyperbolic Pythagorean theorem, which is not the sum of the squares, is the difference of the squares. It's heady stuff, and the funniest part is in the intro, the author says you don't have to have any math background whatsoever. I had multiple degrees, and I barely understood what the heck was going on by chapter 2. It's some pretty heady stuff written by two Cambridge physicists, but it's really cool. But hyperbolic functions have different identities. Namely, the difference in the squares of the hyperbolic cosine and the hyperbolic sine is equal to 1, not the sum of the squares. So that changes things a little bit. But it's some cool stuff. Can I go any further with this answer? No, I'm done. You notice we didn't change anything to e to the x. We don't need to. Only when the argument is a log. Otherwise, you leave this alone, and this is one of the simpler ones, turns out. This is not that complicated. And unlike regular sine and cosine, there's no negatives there, which is way better, right? Okay, we are now done. You now have the antiderivative formula for everything that exists. So I'm going to go back to Cece's question. Why did we ignore the other inverses? And here's why. And by the way, even most calculus books do the same thing. Here's why we ignore the inverse the inverse cofunctions. Because their derivatives are exactly the negative of the other derivatives. So Matt, rather than learn 3 new formulas, if I asked you the derivative of the inverse cosine of anything, the answer is the negative of this derivative. That's why we ignore them. Because all you do is you just do the other one and slap a negative, and that's it. It's actually that simple. And rather than have you learn 3 new formulas, it doesn't make any sense. You just do that. It is actually rare to come up with an inverse cofunction, strangely enough, in terms of the calculus sense. Now, the inverse cofunction is not equal to the negative of the inverse function. The derivatives are negatives. The functions themselves differ by actually not only a sign, but also a constant. Think of like a phase shift with sine and cosine. You remember doing those? You know, the sine wave looks just like the cosine wave shifted pi/2. It's because of the phase shift.
Okay.
Don't worry about it. If you know this, then you don't need to worry about these ever.
Okay.
Literally ever. So you now know all of the antiderivative formulas that actually exist. We're in week 10 of Calc 1. Wait a minute, you've got 2 more semesters, you've got differential equations. Everything's now using these to answer questions and tweaking them and making them more complicated. That's what that is. All right, let us talk about our exam. We have a party coming up on Monday, and it's one of those parties where you're encouraged to show off and strut, you know, and right answers are strongly encouraged, by the way. So the nature of this test is, yes, we have derivatives just like the first test, but we're doing different derivatives on this test. But within your derivatives, for example, the very first problem here, the main thing there is the fact that you have an exponential function with a base of 4. We have a derivative formula for that. That's not one you have to be clever. You don't have to use logarithmic differentiation. We have a formula. It's on your sheet. But aren't I still differentiating sine and secant in this answer? Yes, I am. So are you still doing all your previous derivatives? Yes. I'm just not going to ask you any standalone problems. I'm not going to ask you to differentiate just the sine function. But it might show up in one of the new functions we're doing, like an inverse trig or a hyperbolic, right? Those are the main ones we did. Exponential, logarithmic, inverse trig, hyperbolic. So I like mixing things around a whole bunch. But the first 2, for example, the first one here, the derivative of 4 to a function is 4 to the function, log 4, derivative of function. That's a straight up formula. A lot of us are taking too long. We're doing logarithmic differentiation, which is fine, but we have a formula. Just use the formula. That means you can give the answer. The difference is this is a product, so we had to use product rule. And so you notice in the first step, this was, Albina, your question, I have a secant times a cosine in my first statement. Secant times cosine is 1. So don't factor out a secant, no, you have 1. Right? It'd be kind of like saying, I'm going to write the answer to the question 4 times a fourth plus 3. 4 times a fourth is 1. Why don't I just take advantage of that? Right? I wouldn't write something multiplied by its reciprocal as a final answer. It's just multiplied out. Now the second one, if that were log base e, then the answer is just 1 over function times derivative of function. Life is good. It's not log base e, so the answer is still 1 over function times derivative of function with the log of 6 also thrown in. That's the only extra thing, and we have that formula. The third one's not a formula, it's a technique. You can use logarithmic differentiation, or you can use the e to the log trick and then use exponential versions. They're both about, well, this is actually one step faster, but it doesn't matter. Now the next one, or the next couple, you notice I have inverse tan and I have inverse secant. These are straight up formulas once again. Okay, so inverse secant is going to be what? 1 over absolute value of thing times the square root of thing squared minus 1. Okay, in this case, thing is ugly. Thing is x to the 2/3 power. Yikes. Now, can that x be negative? In x to the 2/3, can x be negative? Yeah, because I'm squaring it and I'm taking the cube root. There's no problem with being negative. Notice my final answer. This is the one exception to most of your formulas. My final answer, when I did all my canceling, I was left with just an x. But if that x can be negative, my final answer we showed with the secant, the final answer can't be negative. But if x can be negative, I have a problem there unless I put the absolute value in. Why didn't I put absolute value around x to the 2/3? Because x to the 2/3 is already positive. But that quotient is not necessarily positive. Now here's one of the beautiful things. I said inverse secant of something ugly, of x to a power. But no matter what, my final answer, my numerator is always going to be of degree 1 less, isn't it? So they're always going to cancel, leaving me just an x on the bottom. And we did some problems like this in class. So it's absolute value of x on the bottom. That one is ugly. But look at the final answer. It actually cleans up a bit. Hyperbolic tangent is just square of hyperbolic secant. And then there's nothing clever. That's just what it is. If I was blind and I didn't even see the h, that's bad, by the way. But if I was, and sometimes I can't see the h. My eyes give me troubles. If I didn't see the h at all, and I did this entire problem, my final answer would look the same without the h, wouldn't it? Think about that for a moment. That's how complicated hyperbolic tangent is. You're going to get the exact same answers, but with an h in them. Don't make that hard. It's not. That was actually fairly simple. Okay, then we keep going. Now, number 8, I love only because you get to do it however you want. This is the problem you really would want to use logarithmic differentiation on. Because I'm starting with an e and I can make things easier. Do I have to use logarithmic differentiation on this one? I don't have to. But notice your final answer is void of e's and logs. That means it's a way simpler answer than if I didn't, and I left e's in my answer. It would be much more complicated looking. Okay? On the exam, like you did on the first exam, this exam has about 1 million questions, but you only have to do some of them. I've given you a bunch of derivatives. I asked you to do some of them. I've given you a lot of applications. I asked you to do some of them. You actually get to skip, I don't know, somewhere between 1/3 and 1/4 of all the questions I have. This is maybe like 30% of the questions. The idea being, I really like giving a test that asks everything that I considered relevant that we went over. But there's no way you're going to finish that test in 2 hours. So you get to pick and choose which ones you want to show off. And I'm serious about that. So you look at 3 problems and go, I know how to do all of those, but maybe I only have to do 2 of them. So I do 2 of them. So what happens at the end of the test when there's still time on the clock? You go back and you do the other one. But only at the very end if there's time. That's called insurance. Now, I can't answer this question, only you could. On the first test, I don't believe anybody didn't do insurance. I think every single person here did extra. Some literally did every problem. Does anybody know when you went back over your test, does anybody know that an insurance question actually counted? One that you did after the fact ended up being one that counted? Did you have one that did? Most people would say they didn't. There's a reason you put it off till the end and then they end up not counting. But the very fact that one even may have counted is all the reason why you did it. Because one of the first ones you did, you messed up, you didn't see it, you did an extra one later, and then that one ended up being the one that counted. That's why you do an extra one if you have time. But only if you have time. If I say here's 10 problems, do 7, don't do all 10. Do 7. Later come back and do another problem if there's time. But if you do all 10 now when you get to the end of the test, you might not be able to finish the test because you just did 3 problems that aren't even going to count. That's not good test taking strategy. Do as many as I said, get to the end, check your answers, and most of you will always have time on the clock to come back and do an extra. The applications are longer and they're more expensive, so you don't have to do that many. But I've asked you, one of the applications is use logarithmic differentiation. Okay, that's one of them. Of course you have an optimization. Of course you have a Newton's method. You have a few of things like that, but you know exactly what I'm going to ask you. And you strategize saying, I know how to do this one, but this one takes me longer. Let me move on to that one. I'll come back to this one. That kind of thing. I love questions like number 10. We know how to do this one straight up. This was exam 1. This is straight up product rule, but it's really messy, especially with that fractional exponent. But if I use logarithmic differentiation, it's actually kind of clean. The only thing I need to do is put over a common denominator. And then at the end of the problem, everything works out nicely. I've asked you one of this nature. And these can algebraically be kind of messy. So this might not be your fastest one. It might be your least challenging for a lot of you, but it might not be the fastest one. Oops, here we go. Now, a huge section of the exam, because this exam is all about literally applications of the derivative. My Calc 3 has their test. Some of you just saw them taking that now. Their test is almost entirely application of the derivative. On their last lecture, they started integration in 3 dimensions. On your last lecture of material, what did you start? Integration. Your test is 8 lectures, 7 of them on applications of the derivative. Their class is 8 lectures, 7 of them on application of the derivative. It's crazy how you guys are exactly aligned. They're just doing it in 3D. So they have all the same issues you guys have at the same places. This is considered hugely important in the calculus sequence. Your ability to analyze graphs. You're not going to draw them. You're just going to tell me everything interesting. You can't tell me an extrema, whether it's a max or a min, without some form of a test. Now, on the exam, I don't ask you to do a specific test. I'm going to say, on this one, I just asked you for extreme. But you have to have some form of test. So I'll say, give me the intervals of increasing and decreasing. So what do? You take a derivative, you set it equal to 0, find your critical values, do your first derivative test, or just shading above and below. Now, give me your intervals of concavity. So you take a derivative, set it equal to 0, blah, blah, blah. You've done both of those. Now I'm going to ask you for extrema. So now you can use either the first derivative test or the second. How do you decide which one to use? How do you decide? Well, the right answer would be whichever one is easier. So how do you decide that? Well, was the second derivative easier to take than the first derivative?
No.
If it's polynomial, it probably is. But if it's a rational function, if it's something complicated, it probably isn't. So you just say which derivative was easier to take, that test will be easier to perform. Now, what if I ask the exact same questions, but I give you a closed interval, which often is the case with application? Can you now use extreme value theorem? That's where you evaluate the endpoints and the critical values in the interval. And on applications, we like that one because it saves us a lot of time, right? Doing first or second derivative test is always correct. But remember, any test you perform, you have to get the same conclusion if you did the test right. So you only perform one test. But you cannot ever come to the conclusion of max or min without testing it. You see, I always remind people, if I have a horizontal tangent, let's take a simple graph. I have a horizontal tangent, and you're trying to determine extrema, and you had a horizontal tangent. So obviously, this was a max. Same question. I have a horizontal tangent. Obviously, it was a min. Same question. Same people. I didn't test it. I have a horizontal tangent. This is why you have to test it. All 3 of those are equally likely when you have a horizontal tangent. You can't tell me it's a max or a min without testing it. It could be either one, and it might, and this is an either, isn't it? Probably an inflection point. Ooh, so that's why I gotta test it. Something simple. Now, the nice thing is about number 11 is I gave you a closed interval. You don't have to do any tests. You can use extreme value theorem. That's endpoints and critical values in the interval. That's why we calculated things. Now let's go to 12 to 15 is the more common one. This is about as generic as it gets. I'm giving you a cubic. It's probably changing direction a couple of times. You took derivatives, set it equal to 0, life is good. I made my G prime number line, figured out where it was positive, where it was negative. Boom, that's how I answered the question. I can ask for extrema, or you can tell me extrema right now. Where it went from increasing to decreasing, I gotta have a max. Where it went from decreasing to increasing, I gotta have a min. I didn't ask yet. I now ask for intervals of concavity. Boom. Where I change from concave up to concave down, that's where my inflection point lives. So now I have inflection points, and you notice the last thing I asked was extrema. You could have used the first derivative test or the second. Don't worry about absolute versus local. Believe it or not, that was a major question today in my Calc 3 class. They do this in 3D. But how do I determine absolute and local? I said, that is the easiest part of any problem. I can tell you that answer before I do any of the work in the problem. I can always tell you before I do anything, because that has nothing to do with calculus. Go back to the question, what do you notice? It's x cubed. So as x increases, it's going to go up forever. As x decreases, it's going down forever. Am I going to have any absolutes? No. That's it. If you did anything other than that to make your conclusion, then it was an outright guess. It's going up forever. Can't be any absolutes on maximums, only locals. It's going down forever. Now, what if the lead exponent was even? And let's say positive coefficient. Then whether x is positive or negative, it's going up forever. Think parabola. No absolute maxes, but I'm definitely going to have what? An absolute min. Same thing if it's pointed downwards. There won't be any mins, but there will be max. Can you simply look at exponents to make that kind of conclusion? When it's polynomial, yes. That's not calculus. That's not calculus at all. And a lot of times we're looking for the wrong thing. We're making that complicated. Now, max is way more important than local versus absolute. So if I'm asking you for extrema, let's say it's a 10-point question, and I'm asking for extrema, and you said local max when it was absolute max. That's a couple points. But if you said min, that's the whole problem, because that's the wrong answer. Local versus absolute is minor. I'd like you to get it right because it's not that complicated, but max versus min is way more important, okay? Because you've got to use some form of a test to do that. All right, so let's move down. Now, asymptotes. I have some questions where I just simply ask for asymptotes and nothing else. So now there are 3 types. There are 3 types. Probably the easiest one for most of us is the horizontal. Because what am I looking for when I'm making that conclusion? The degrees. Same degree, there's a horizontal, and it's y equal a number. What if the numerator is smaller than the denominator?
0.
Then y equals 0, the x-axis. It's y equals 0. What if the numerator is bigger than the denominator? Then there's no horizontal. It grows without bound. What if the numerator is exactly 1 higher than the denominator? Then there will be a slant. Can there be a slant and a horizontal at the same time? No, because a slant means it's 1 more, horizontal means they're the same or it's less. Now, vertical has nothing to do with those other 2. Vertical is you're just looking at the denominator. Wherever the denominator is 0 and the numerator is not, a removable discontinuity is not an asymptote. So if it's factorable, you probably want to factor both of them, like in number 16. Look at number 16 for a moment. If I didn't factor the numerator, am I likely to say both x equal 1 and x equal negative 1 are asymptotes? But because I factored the numerator, I realized, oh, that's just a whole. That's not an asymptote. Yeah, Cece.
For the slants, right, when we're stating the y line that it looks similar to, for the transient term on the side, do you want us to just mark that off and be like, oh, this is, transient term is just always.
Oh, when you're doing your long division, see, I don't know if 6. Okay, let's look at 17. That's probably better. On 17, I did the longer synthetic first. My function is asymptotic to x plus 2 because the other term is a transient term. But h of x is not an asymptote. H of x is the function. So I actually want to state specifically that y equals the line. The line y equals x plus 2 is my asymptote. Many of you, and I appreciated this, you guys got very mathy, and which is never a bad thing, but sometimes we overkill. My h of x is equal to x plus 2, oh, maybe just look over here. We call this a transient term. Its contribution lessens as x gets bigger. When I graph the line and I graph the function, immediately the function disappeared into the line. We've done this before. This is a correct mathematical statement. This function is asymptotic to this line, but the function is not the line. So I don't say, I have not stated my asymptote yet, but I've told you what the asymptote is. The asymptote, therefore, is the line. H of x is not a line. It's asymptotic to a line. So I want you to tell me what the actual line is. That's what I think you're asking me.
Yeah, okay.
Okay, so I loved it that people did this, but we never actually finished the answer if I'm stating that. Can I be asymptotic to a parabola? We've done that before. Yeah, but that doesn't mean my function is the parabola. That just means graphically it disappears into it. I can't tell the difference. I like that. It makes math a little easier sometimes. So vertical comes from the denominator. Has nothing to do with horizontal or slant. Everybody okay with that? So if it's factorable, factor it. The second one's easy. You only have one quotient, 1 over x minus 1, so my vertical is x equal. Your asymptotes are lines. So please don't, I'll get this answer. And the asymptotes are 3, 5, and 7. I don't know what that means, to be honest. Oh, the 3's vertical and 5's horizontal. Those are scalars. Those aren't lines. No, I need x equal, I need y equal. Asymptotes are not numbers. Asymptotes are lines. So make sure you finish the answer. Horizontal is y equals. Slant is y equals. Vertical is x equals.
So for like 16, when we're doing the horizontal, do you want us to show like limit x approaches?
No, but I'm telling you that's where it came from.
Okay, cool. Like, 'cause I could go like just straight to 3.
You could look at 16 and say they're both second degree. I know we've shown this in class. We showed this in class on like the 3rd or 4th day of class. That if I take that limit, this is where you'd multiply top and bottom by 1 over x squared, get your transient terms, and you show the limit as a constant. Beautiful. I'm doing the exact same thing here, but I'm canceling first. And I did that for the sake of the vertical. If I only asked you for the horizontal, would I need to do any of the algebra on 16? No. But because I asked you for vertical also, you needed to do the algebra because otherwise you wouldn't have seen the cancellations. So you don't have to tell me the limit, but I'm telling you that's where it came from.
Oh, never mind, that was my question.
I'm showing you because a lot of times everybody here can do the vertical. And nobody thinks of a limit when you do a vertical asymptote. No one ever thinks of that. But a horizontal asymptote is the result of a limit to infinity. It can't be anything else. So I'm reminding you of what it actually meant.
So just making sure, right, on the exam, I can write, since the degree of the numerator is equal
Yeah,
to the
yeah.
degree. Okay, thank
Yeah, that's, you want to make sure because again, the 16 and 17 look very similar, but one has a horizontal, one has a slant. Can I have more than one horizontal? Can I have more than one slant?
No.
Can I have more than one vertical?
Yes.
That's not a trick question. I gave a quiz where I asked for asymptotes, and I actually had more than one answer of you can only have one vertical when there was more than one. And I'm not sure where that came from, but that would be a misconception, obviously. Now, number 20. I'm using the same one as 17, by the way. I love this one. We did this in class. Remember, this is the one that had two bulbs? And as when we step back, it looked like a line after a while. So I'm going to ask you this question on the test. Do the asymptote first. Because to do the asymptote, you got to do the longer synthetic first. That's the thing you want to differentiate. Don't differentiate the quotient. It's too much algebra. And by the way, I asked this on a recent quiz, and a lot of you correctly differentiated the quotient. But it took so many steps of algebra, and then you had to factor, and it was really busy. And what's worse is you then differentiated something more complicated for the second derivative, and a lot of times it kind of, burned and crashed and fizzled and no, differentiated in the differentiate it in this form, and then you get this. And then when I differentiate this, this took me about 1.5 seconds to differentiate this and get this. There's no work whatsoever. But if I leave it in the quotient form with all the factored terms, I'm using quotient rules and chain rules and product rules, and it's really messy. Do you agree? Those who did it that way went, oh my gosh, you mean I could have done it simpler? Yeah, so I think on the exam, I ask you a question like this, and I think I start with the asymptote. Just like wink, wink, do the asymptote first. Then when you do your derivatives, you're differentiating easier things along the way. Now, what made this one particularly interesting, if you remember, was the max was lower than the min. Because it had two sections and did that. That's why that was the case. So you have to do some sort of a test, obviously. Now, on this one, interestingly enough, I had many people tell me that, for this problem, that x equal 1 is a critical value. X equal 1 is not a critical value. Why?
It's an asymptote.
Yeah, so go back. Why is x, look at the original function.
It's not in the domain.
It's not in the domain. What's confusing is when we did problems with cusps or vertical tangents, the derivatives were undefined, did not exist at the value, but the function did. That was the evil critical value. The function existed, but the derivative did not. That was particular to cusps and vertical tangents. But if I've got a vertical asymptote, it's not even in the domain. It can't be a critical value because the functional value doesn't exist. And so I had a lot of people telling me the vertical asymptote was a critical number. That's not correct. We're confusing it with the cusp. So a wise thing to do pretty much in all problems that are applications, always start with stating the domain. Not for me, for you. If you told me the domain was all real numbers except 1, then 1 can't be a critical number, can it? Do you agree? But what if this was such a problem that the domain was all real numbers? And now the derivative doesn't exist at 1? Oh, then 1 would be the evil critical value. That's okay. That's like the cusp. A lot of us got those two confused. So I don't want that. Now, the nice thing about 19, it's never 0. I don't have an inflection point because it changes concavity at 1, and 1 is not in the domain. But because it changes concavity, I have a section where it's up, I have a section where it's down. Did anybody graph this on their own to see what it looked like when you were doing the problems? It's probably a good idea. Like I always said, you did all the calculus, you answered the questions, what the heck did I just say? In other words, what was I answering? So to go to Desmos or something to see what this looks like, you go, oh, that's why I said that. Okay, it's really obvious now. That's a good thing. Okay. Now, I love this question. All right. I did not do this in class, and I feel remiss. I usually always do this problem in calculus. All right. Does anyone here have kids? Okay, how many of you were kids? Kindergartners at one point. All right, I've been parent helper more times than I can remember in all of my kids' classes. Kindergarten's the most fun. And so here's the typical situation. The teacher had these gigantic pieces, always colored, the really stiff paper, I don't know what that's called, but the really stiff colored paper. You guys remember that? Your kids. What's it called? Probably construction paper. So they all have the construction paper, and they're going to make a box. And I'm giving them the piece of construction paper, so the teacher would ask me to cut things out. I hated doing that. I'm just really not good with scissors. So I'm giving you a piece of construction paper. And I'm going to ask you to construct the largest open box you can construct. That's what I'm asking. How the heck do you do that? I'm not joking. We did this. I have generations of kindergartners who can now pass this test because they did this problem. This is exactly how you do it. I should have done this in the lecture. I didn't have time. Now what do? I fold. I fold. No, it's not going to be a paper airplane. It's an open box. It works way better with scissors, by the way. Now, how many different size squares could I cut out? Infinitely many, correct. Would they all produce the same volume? No, everyone would be different. I need to know how much of a square to cut out so that when I make this, I have the largest volume possible. Do you understand that? In this case, I asked about surface area. I could have asked about volume. Wouldn't have made any difference. The point being, I'm taking a something that's flat and doing it that way? That's a cool question, isn't it? So this is the one, parent helper, I cut out the squares, although I don't imagine any of my squares are exactly the same. The only rule on this one is all the squares need to be exactly the same. So you would do that. That is a calculus problem. So in this case I said, I'm giving you the volume. So it's different. We are building this building. We have the materials, we know the volume we need for the classroom. The cost of this classroom is not based on the volume. It's based on what? The surface area. That's the materials I'm using. The volume is the air. When I'm building the room, it's based on the surface area. I have to pay for the walls. I don't have to pay for the air. So what I'm trying to do is, given a certain amount of volume that I need, I want to minimize my cost. But let's just pretend for a moment that all the walls cost the same. They don't, but let's just pretend they cost the same. Then minimizing my cost would be equivalent to minimizing my surface area. Do you agree? There's an infinite number of possibilities. See, I could have a football field sized basin that's only an inch tall. Same volume. Big surface area. I can make it really narrow and long. There's infinitely many ways I could do this. I want the minimum surface area. That's my goal. So that's what this problem is designed to do. It's the same as almost as that problem. It's a great question because we can do it using nothing but what we've learned in this class, optimization. Oops. Now, we did two versions of the estimation. We did it using geometric shapes where we are doing what's called the relative error. And we did it where I gave you a number and I said, hey, can you estimate 2.99 to the 10th power? So what'd you do? You used 3, and then you used the differentials, you added it, and you got a number that was really close, and of course you checked it on your calculator. Those are the only two versions of the question, a numerical value or a geometric thing. I'm going to ask you one of those, not both. Okay? Let me really quickly finish because we're about out of time. This is the mean value theorem. Most everybody did a good job, and I think one person told me whether it satisfied the hypothesis. You don't say, yes, it satisfies the hypothesis. What's the hypothesis? You have to be differentiable over the open interval and the endpoints have to exist. That's a major thing. This function is not differentiable everywhere, but is it differentiable from -1 to 8 over the open interval? Yes. It's not differentiable at -1, it's differentiable at the open interval, and then -1 if I plug it in works. This satisfies the hypothesis because it's differentiable over that interval and the endpoints exist. That's what the hypothesis is. By the way, when I ask that question, it's got to satisfy the hypothesis. Because if it doesn't, you won't be able to finish the problem. Then it's really boring. And finally, Newton's method. We did this in class. Now, you did everything right. You got that answer. How do you know you did it right? I got this answer. How do I know this is right? Put it into the function. Are you going to get back 0?
No.
This is a rounded off value, so no, but are you going to get something really close?
Yes.
Yeah. Hopefully you got decimal point and some zeros close. Okay, I would hope that everybody automatically checked your answer and said, oh yeah, this is like 0.000 something. Okay, good. You're not going to get back exactly 0 because the answer is irrational and you rounded it to 3 placements. You can't get exactly 0. But you ought to be really close. Now, there will be some integrations, and I promise you, they are all simple. Meaning, there is no substitution at all. Every one of these you can do, but on the first one, you got to change them to exponents, as you know. Okay? Second one, you got to use a trig identity to make sure you have the right trig. But you know both of those antiderivatives, don't you? So, what are you going to bring to the test? I would bring all your derivative formulas. Because even though I'm going to ask you, hyperbolic sine and cosine, I'm going to ask you inverse tan. What if I asked you inverse tan of e to the x? Oh my gosh, I forgot e to the x. Hopefully you didn't. But I can ask you any of these of anything, have all of your derivatives there, then you don't need to write down, by the way. You won't need to write down any of your antiderivatives. Because if it's a derivative from left to right, then it's an antiderivative from right to left. So for this test, your derivatives will already have the antiderivatives. You don't need to do it twice. But you need to write down the formula for Newton's method, for example. Right? That's a very specific formula, one to get it right. You don't have to do every problem. You get to choose, but you definitely want to operate to your strengths. Okay? Let's go ahead and turn on. I think we're probably done recording anyway.